Good evening, and thank you for joining this webinar. We'll get started in just a few moments to allow those people to come into the Zoom meeting room. But while we wait, we're going to put a question up on the screen, and we're looking for you to answer that question, and we'll use the results later in our talk that Chris is going to give us. So if you've just joined, please answer the question. Hello, and welcome to How, Why, and Where of Nuclear Waste, educator seminar presented by the American Nuclear Society. This evening's event is part of our educational training program specifically developed for elementary through high school teachers. My name is Eric Lowen. I currently work at GE Hitachi Nuclear Energy as the chief engineer and manager of the chief engineer's office. And I have always been associated in my professional career with the American Nuclear Society, which culminated in me being president of the society in 2011, 2012. So with that, a little bit of background, and before I introduce our presenter, I'd like to cover a quick notes for today's seminar. If you have any questions, type them into the Q&A function of Zoom, and we will answer as many questions as possible. The event is being recorded, and the recording will be emailed to all the event registrants, so you can use this in your classroom or refer to it. Certificates of attendance for today's webinar are available upon request. Please email us at askanything@ans.org to get a certificate. If you'd like to learn more about other ANS educational events, programs, and resources, you can visit our website at ans.org or email our senior manager of STEM programs who's supporting this, Uchenna Azibe, and his email is being put into the chat. For educators in the audience, please let us know if you'd like to have an ANS member to actually come visit your classroom. We can do it virtual or in real life. We have volunteers that we can send out. Just send your request again to that email, askanything@ans.org. Finally, we ask all participants to adhere to the ANS Code of Ethics and Respectful Behavior, which we have on our ANS website, and Uchenna is going to put that link into the chat. So now I'd like to introduce tonight's presenter. Dr. Christopher Perfetti is an associate professor in nuclear engineering at the department at University of New Mexico. Prior to his appointment at University of New Mexico, Chris was a research scientist at Oak Ridge National Laboratory, where he served as the sensitivity and uncertainty analysis methods team leader for a program called SCALE. And if you want to ask him more about that program, you can get a hold of him. By 2008 in his life, he had received a BS and MS degree in nuclear engineering from University of Florida. And then in 2012, he received a nuclear engineering PhD from University of Michigan, go blue. His research interests include uncertainty analysis, method development, Monte Carlo method development, advanced reactor core design, nuclear criticality safety, radioisotopes production, and radiation shielding. He's also very active in our society. He has served as chair of the American Nuclear Society's Reactor Physics Division, chair of the Alpha Nu Sigma National Honor Society. He's been chair of 2 local sections, both in New Mexico, the Trinity, and at Oak Ridge, Tennessee. And currently is serving as the secretary of the American Nuclear Society Education Training and Workforce Development. In his free time, Chris enjoys cycling, hiking, and taking his daughters to museums. And you're probably wondering why. He's also the chair of Adult Education Committee at the National Museum of Nuclear Science and History. So with that introduction, Chris, I turn it over to you.
All right, thank you so much, Eric, and thank you everyone for joining our lecture tonight. This is uh, nuclear, I call it Nuclear Waste 101, but it's the how, where, why, and the everything of nuclear waste. So we'll start by a question, which I believe you should see as a poll that's coming up to try and engage how many folks, what knowledge we have about nuclear waste in the audience. But the question is, how much nuclear waste is there? About how many metric tons of nuclear waste has the US produced since it began producing commercial nuclear energy? So please go ahead and answer this question in the chat while I continue introducing myself and presentation. And I believe that I will have the answers to these available to me so I can tailor this talk based on what folks know or don't know. All right. So again, about me, Eric basically said all this. I am a assistant or associate professor at the University of New Mexico after this history at Oak Ridge and Michigan and Florida. I will mention that my research, my professional research, is on Monte Carlo methods, radiation transport, reactor physics, nuclear criticality safety, some isotope production. It's not especially on nuclear waste. So why am I giving this lecture? Well, I have a online YouTube series on nuclear waste. It also covers each of my 3 courses at UNM. The channel has several 150,000 viewers right now, so I'm happy to see that number growing every day. But I guess it means that I'm actually a YouTube celebrity who's giving their opinion on nuclear waste, not necessarily a nuclear waste expert. But I see this presentation as appealing to 3 audiences. The first group is like folks like high school science teachers who don't necessarily know that much about nuclear waste, but would like to learn more. Let's see. All right, looking at the Q&A. The second group is nuclear engineers who know a little bit about nuclear waste, and this presentation may fill in some gaps in their knowledge, and also it might help them have effective talking points so that they can answer questions about nuclear waste quickly and effectively. Next Thanksgiving, when your cousin asks you about, well, what about the waste? Maybe you'll have an answer on hand. And then the third group, the group I fear the most, is experts in nuclear waste who know much more than I do. And I actually, I think that y'all will probably enjoy this presentation as well because I go into several non-traditional approaches for disposing of nuclear waste that might not be on your radar. So let's get in. Let's dive in. So here's a brief outline for this presentation. We'll start with what is nuclear waste, go into how much waste is there, how can we fund waste disposal, and then how can we dispose of it? So here are 4 options for disposing of nuclear waste that I will review during this presentation, and there's also a hidden secret 5th option that we will review. So starting next, what is nuclear waste? Is it this glowing green sludge like you see on Captain Planet, or is it something else? Well, actually, audience question number 2. I think some folks said in the chat that the Q&A might not be working. I'm not sure, but uh, what does nuclear waste look like? So is it a solid ceramic material, a glowing green liquid like from Captain Planet, a black powder similar to coal ash, or a thick radioactive sludge? So you can vote now for the answer to this question. Well, so nuclear waste there are several types of nuclear waste, but when people say nuclear waste, they generally mean used nuclear reactor fuel. So nuclear waste is typically thought of as, oh, here's our poll. Nuclear waste is fuel from a fission nuclear reactor that has finished up being in the reactor. It can't produce any more energy, so we take it out. Answer question number 2 quickly because I'm about to give you the answer. Well, actually, I'm 1 slide ahead. So the PC term for nuclear waste is actually spent nuclear fuel because it's not waste, it's just used fuel. And actually, an even better term is used nuclear fuel because saying it's spent implies that there is no value left in the fuel. As we will see later, there's actually quite a bit of value left in that fuel. So nuclear waste, to answer that question, it is actually a solid ceramic material similar to a teacup or a dinner plate. So like our character from Beauty and the Beast right here. And it actually looks more like this. So here's a uranium fuel pellet, uranium oxide fuel pellet. They're about as big around as your pinky finger. And when they go into a nuclear reactor, they are stacked on top of each other to form fuel rods. They're stacked on top and then encased in zirconium metal to make these fuel rods. And we group these fuel rods together into fuel assemblies, typically in like 17 by 17 lattices, or if it's a BWR, 9, 10, or 11 by 11 lattices. But we make these groups of fuel, and then the reactor itself contains about 200 of these fuel elements. So you can see a fuel element right here in a spent fuel storage pool. This is where the fuel goes after it leaves the reactor. It stays here for some time, and this is what it looks like. This is a picture of actual nuclear waste sitting in that spent fuel pool. So it's not a glowing green sludge. It's just blue because the water is blue and it has lights in there. This water is actually quite pure, but it's just this solid uranium pellet in metal inside of this fuel pool. So it's nuclear waste is not what a lot of people think it is. It's not some sludge that's in barrels or something. So why is nuclear waste dangerous? It's important to know this because it informs how we deal with waste. So nuclear waste is dangerous because it contains radioactive fission products. So what happens is when uranium atoms absorb a neutron and fission in a nuclear reactor, they break apart. They release some neutrons, and then they turn into several smaller nuclei, usually 2 or 3, which tend to contain more neutrons than they would like to contain to be stable. So because they're unstable, they're radioactive, and they can release radiation as they undergo radioactive decay. There's quite a big distribution of fission products we can get from nuclear reactor. So it's not just krypton and barium, it's all sorts of different things that span quite a few elements in the periodic table, actually about 400 different isotopes in spent fuel. So it's quite diverse, a lot of these radioactive things. Now, this nuclear waste, it's dangerous because it's potentially radioactive and can emit radioactivity. So our goal here in disposing of nuclear waste should be to isolate it or contain it somewhere safe until it undergoes radioactive decay and becomes radioactively inert. So this is interesting because in some ways nuclear waste is it's quite unique amongst forms of waste in that it actually gets easier to dispose of nuclear waste over time because it just gradually becomes less and less radioactive. All right, so how much waste is there? So to answer that first question, it's 88,000 metric tons of waste, and which actually really is not that much waste. Yep, so there's that question one again. So we don't have that much nuclear waste.
Chris, just quick question, Chris. I'm sorry to interrupt. Are you able to see the results of the question that the audience has answered?
No,
Okay.
yeah,
I think it's because you're screen sharing, but I can read it out for you or put it in the chat.
okay, yeah, I will ask you the results of the polls throughout here. I
Yeah,
guess,
because I can't see it either, Uchenna. So something's showing up.
Interesting.
Yep.
Okay. Okay.
Yeah.
All right, we'll take a look at why that is, but I will read out the results of everyone's voting when you're ready. So you just let me know.
cool, all right. I guess, well, guess we could go to how many folks got the first question right about the radioactive sludge, or I guess the second question. I believe you are on mute, Uchenna, if you'd like to read out the answer to question two.
Will do. So 72% said a solid ceramic material, 2% said a glowing green liquid, 12% said a black powder similar to coal ash, and 14% said a thick radioactive sludge.
Okay, cool. Yeah, 70 some percent is pretty good, but hopefully the the radioactive sludge and the well, hopefully the wrong answers. Maybe you learned something about the form of nuclear waste. And how about for question one?
For question one, 14% said 88 metric tons, 23% said 8,800 metric tons, 53% said 88,000 metric tons, and 10% said 880,000 metric tons.
Very cool. Well, you all have gotten the majority has gotten all the questions right so far, so good job to the audience. All right. So how much waste is there? So really, there's not that much waste. That 88,000 metric tons is not a lot. And that's because nuclear power is actually quite efficient. So it's efficient because one coal combustion reaction releases 4 electron volts or 4 eV worth of energy, while one fission reaction One uranium fission releases about 200 million electron volts of energy. That's a factor of 50 million in difference between the two numbers, which means very approximately that nuclear power plants need to use 50 million times less fuel than a similarly sized coal combustion plant. So nuclear power plants are actually quite efficient because of that. So the fuel in the nuclear reactor actually, those fuel assemblies that we saw before, right? They stay in that reactor for 3 18-month cycles. So on average, after 54 or so months, they leave the reactor and go into the spent fuel pool, which is 54 months is a super long time, whereas a coal power plant will get another shipment of coal every day, pretty much in these big long train cars. I've had the misfortune of being stuck behind one of these train cars when it passed. I was driving around Crystal River, Florida, years ago, and the train car had 97 cars of coal that it was loading up for the day's use at the coal power plant. So it's much less efficient than the nuclear power plant because each reaction releases that much more energy. So because of that, there's really not that much nuclear waste. If you were to take that 88,000 metric tons and turn it into a cube, it would be about this big, which if you stacked it in the fuel assemblies, it would about cover one football field. So that's, I mean, that looks kind of big compared to the stadium, but really this is not much waste at all. This is a teeny tiny amount of waste. Well, it's small because you need to consider that this waste is from 50 or 60 years of nuclear power in the United States. And during that time, nuclear power generated on average 20% of our country's electricity. So 50, 60 years of 20% of our electricity has only generated this much waste. That's actually really impressive. I mean, it looks like a big cube here, but really it's quite small when you put it into perspective. To do that, to put it into perspective, consider that every year annually, the United States releases CO2 emissions that are 76 million times the volume of this. So 76 million of these cubes per year in CO2 emissions. So nuclear power is quite efficient on the waste. So how do we pay to dispose of nuclear waste? Is there a mechanism? Turns out there is. In 1982, the Nuclear Waste Policy Act established the Nuclear Waste Fund, which funds nuclear waste disposal by charging a tax of 1/10 of a penny per kilowatt hour of nuclear energy produced, which, considering that this is the average electricity price, right? This is a very small fraction of our electricity prices used to fund nuclear waste disposal. If your household ran on about 100% nuclear power, you would pay approximately 90 cents per month for this tax. So that's, my electricity bill was $250 last month. An extra 90 cents to pay for nuclear waste is nothing. So it's a quite a small tax, but it generates quite a bit of money, about $750 million per year, which goes into this nuclear waste fund. As of 2021, this fund had a balance of $44 billion. So there is quite a bit of money there to fund nuclear waste disposal. And that 44 billion has actually already subtracted out the 11 billion that we spent designing and rebuilding Yucca Mountain. So there's a lot of money left over to contemplate how we want to dispose of nuclear waste. So that's our goal here. We have $44 billion to spare, and we want to figure out how we should spend it to dispose of nuclear waste. So these are the options we'll review, and the first one is deep geological repositories, which are perhaps the most popular option. So question 3, what was the proposed US site for long-term nuclear waste storage? So feel free to answer that question, and I will start introducing deep geological repositories. So the goal with deep geological, sorry, I can't say it, with deep geological repositories is to place the waste somewhere safe underground, somewhere in geologically stable rock formations that will contain the waste until the radioactivity in the waste has decayed away. If you keep it for long enough, then the waste will gradually become radioactively inert and cease being waste. There are rock formations that are billions of years old that have been geologically stable during that time, so there are some potentially very good places to put this waste. One such place is Yucca Mountain, which was the proposed US spent fuel repository. Uchenna, if you want to read the results of that poll, that this is a good time.
All right, we have 4% for Hanford sites, 6% for Oak Ridge National Laboratory, 2% for Savannah River sites, and a whopping 89% for Yucca Mountain.
Very impressive. Good job, audience. So, yep, as you all already know, Yucca Mountain is the proposed U.S. spent fuel repository, or at least it was. Its status is not looking good for the future, but it is actually in Nevada, just on the end of the Nevada test site where we detonated all of our nuclear weapons in the United States. So I'll go into Yucca Mountain some more. But first, let's look into how long the fuel would need to stay in Yucca Mountain until it is no longer dangerous. So how long would the waste need to reside in Yucca Mountain until it is, or until it can be considered safe? So here's a plot of the sources of reactivity, the different isotopes that contribute to reactivity in spent nuclear fuel as a function of time. You see that some things decay way more quickly, some things last a longer time, and you see how the total decreases over time. This is from a IEA report in 1992. This line right here is a very interesting line. It corresponds to the natural radioactivity present in a ton of uranium ore. So I think this is for a ton of waste, this plot, and then that's the radioactivity for naturally occurring uranium ore, which is also known as yellow cake. Actually, wrong image. Let's try that again, which is actually known as yellow cake. That is the natural uranium ore. And again, this ore is just, it's present in the ground. It's naturally occurring. We're not trying to store it or contain it or dig it up because it's contributing a lot of radioactivity. It just naturally occurs everywhere in some concentration. And there are uranium ore deposits that we mine to get fuel for reactors. So I would argue that this point right here, where the waste is as radioactive as your naturally occurring uranium ore, is a fair cutoff. Right? If it's as radioactive as naturally occurring material, I would argue that it's no longer of concern anymore, that it is reasonably safe. This point corresponds to about 2,000 years. So I would argue that you should design storing the waste for 2,000 years until it is essentially stable. Can we store the waste for 2,000 years? I think so. So these waste packages are designed to be quite tough. You're not just digging a hole and dumping, rusty barrels of sludge in there or anything. This waste it's stored in these big, thick metal containers right here. This is designed for a Swedish container. This container actually has a big, thick layer. This is very, very thick copper around the container here, which copper prevents corrosion. And then the waste is put into engineered tunnels. So the goal here is to prevent water from intruding, from dissolving these canisters, dissolving the waste, and then leaking into the water table. That's the main mechanism by which these radioisotopes could leak out and cause a dose to the public. So these containers are designed to prevent corrosion. This copper is extremely corrosion resistant. And these tunnels are also designed to prevent corrosion, to prevent water intrusion. There are drip shields around these casks so that if water does leak in here somehow, it's not really going, it's designed to drip away from the containers and not actually start corroding them. So these containers, they're very, very rigorous. You're not just throwing it in a hole in the ground. I think that Yucca Mountain might be the ideal location for disposing of nuclear waste, both because I argue that nuclear waste has a relatively moderate storage time, 2,000 years, because these containers are durable, highly engineered, they're really strong, really thick containers. Yucca Mountain is a fairly geologically ideal location. It's in the middle of the desert, so there's not going to be that much water around. So it's quite good because of that. It's on the Nevada test site, so it's quite remote already. Here's actually where it is on the Nevada test site. And I will say I believe in environmental justice. I do not believe in putting a disproportionate toll from any industry on any specific environmental region or any group. But with that in mind, I will say that Yucca Mountain is kind of in the middle of nowhere. It's fairly remote. I've driven past it once, and it's a very remote location. Again, the Nevada test site is where the United States performed 928 weapons tests, including 100 above ground weapon tests. So it's a pretty isolated location. And what's more, the groundwater beneath Yucca Mountain actually flows in, it's part of the Amargosa River Valley, which actually flows through Death Mountain, or not Death Mountain, thinking of Zelda for some reason, through Death Valley. So Death Valley is fairly sparsely populated, so it's not like the water table from Yucca Mountain flows into New York City or something. It flows into a region that's very sparsely populated. So I think that Yucca Mountain is potentially an ideal location for nuclear waste disposal. Uh, to, Spoiler alert, I think Yucca Mountain would be just fine. So you could end the presentation right here and start your Thursday afternoon early, maybe. But it turns out that scientists have actually studied the dose that you would get from disposing of waste in Yucca Mountain. Now, the EPA created some dose limits, which have some interesting political legal battles behind them. How they converge on these dose limits is very interesting. I discuss it. I go all through it in my YouTube channel. But these are the dose limits: less than 15 millirem per year for the first 10,000 years of nuclear waste disposal, and then less than 100 millirem per year after 10,000 years. So scientists from Sandia National Laboratories have simulated waste at Yucca Mountain, and they estimated the actual dose limits, the actual doses that you would get from this waste. And they found that it would be about 0.3 millirem per year for the first 10,000 years, and then 2 millirem per year after that. So this is this is very interesting because we are a factor of 50 below these dose limits. So as far as the dose limits are concerned, Yucca Mountain is extraordinarily safe. The report, which you can Google, is very, very interesting. It breaks down the different sources of that dose. One of the main ones is igneous intrusion, where magma intrudes and melts through the canisters, thus removing all that protection around the spent fuel. But you can look at all the different mechanisms there and see which ones contribute the most to the dose. It's really interesting if you want to be geeky for a few minutes and read the report. But in any case, the takeaway here is that the dose from Yucca Mountain is a factor of 50 below the actual dose limits, which is extremely safe. What's more, I would argue that these dose limits that the EPA established are extraordinarily conservative, perhaps by a factor of 100. So the average dose rate per year for someone in the United States is about 300 millirem per year, about 1 millirem per day. And if you move from one side of Albuquerque, where I live, to the other side of Albuquerque, you can change your annual dose rate by 200 millirems per year just by moving. So we don't regulate that, right? 200 plus or minus 200 millirem per year has no health effect, has no observable health effect. So 100 millirem per year is actually it's like absolutely nothing. It's a very, very low dose limit. If you get a chest CT scan, you get 700 millirem of dose, which some folks in the audience probably didn't even realize that you get dose from CT scans. In fact, the minimum dose shown statistically to increase risk of cancer is 10,000 millirem, which was actually determined by looking at folks who had survived the Japanese atomic bombs. They looked at where people lived versus where the bomb was detonated to figure out the dose they got. And they tracked their cancer rates over the year to see at what point dose increased their cancer risk. So I would argue that maybe 10,000 millirem per year is a better limit than 100 millirem per year. But in any case, these limits are extremely conservative, and we're a factor of 50 below them. So I think it's very fair to say that Yucca Mountain is a very safe way of disposing of waste. So let's go one step further. What is the absolute worst that can happen? Let's get a little silly here. So what if we bury the waste in a non-ideal location, right? Not Yucca Mountain, not something in the desert. Let's bury the waste in a location that has groundwater nearby so that we can transport the radionuclides to the water table. And instead of using these thick engineered canisters, let's just not use anything at all. Let's just dig a hole in some random spot and dump the waste in the ground and see what would happen. It really would be interesting if nature had performed this experiment for us, where it watched how radioisotopes moved over the course of several billion years away from where spent fuel was located. Well, it turns out that this experiment actually has happened. It happened in the Oklo mine in Gabon, Africa. So the Oklo mine is very interesting because it is the location of the world's, as far as we know, the world's only naturally occurring nuclear reactor. So about the uranium enrichment was higher 2 billion years ago. That's because the type of uranium that likes to undergo fission has a shorter half-life than the type of uranium that does not. So 2 billion years ago, the uranium enrichment was around 5%, which is around what we use in nuclear reactors, which means that you could have a naturally occurring nuclear reactor. And that happened at Oklo because there are uranium ore deposits that were surrounded by sandstone and in the presence of groundwater. So that caused the world's only naturally occurring nuclear reactor. I think French surveyors discovered Oklo because they noticed that the uranium was slightly depleted and that there were some fission products around it. It was very interesting. But this Oklo reactor ran for about 100,000 years at a very respectable power of 100 kilowatts. That's quite a bit of energy released. It's a ton of energy released over that amount of time. And the French surveyors looked at it and they figured out how far the different radioisotopes traveled after 1.7 billion years with absolutely no containment, no engineered structures, in the presence of groundwater, absolutely nothing protecting anyone from the spent fuel and from the radioisotopes. What they found was really interesting. They found that some fission products basically did not move at all from where they were created. They just stayed right there. And they found that others moved at most several meters from where they were created. So this is a very this provides even more evidence that Yucca Mountain is extremely conservative, because Yucca Mountain is, I think, like it's 600 to 700 feet below the surface and like 1,000 feet below the water table in the Amargosa River Valley. So if these fission products moved at most several meters, they're not going to move 1,000 feet to reach the water table, and that's assuming that the canisters break. So really looking at the worst case, I think it puts it into perspective, and it really shows how safe Yucca Mountain potentially is. So as far as I'm concerned, Yucca Mountain is a great way to dispose of nuclear waste. There are options, and I think that there may be better options than that. One such option is to reprocess the fuel and use fast breeder or burner reactors. So that brings us to question 4, which is what percentage of spent nuclear fuel has undergone fission? 3, 5, 10, or 50%? I think you can go ahead and vote real quickly because I think the answer is on the very next slide. So Uchenna, if you want to read it. Oh, I guess you can read it now since I just gave it away.
All right, so we have 38% said 3%, 35% said 5%, 19% said 10%, and 8% said 50%.
Cool. All right. So I think the majority has it again this time. And
Actually, the 38% for 3% and
38%.
35% for 5%. So
Ooh.
slight leaning for A.
Yeah, and there's some questions slightly loaded because some fuel is actually only 3% fission for some of the less efficiently used fuel nuclear reactors. But for the most part, about 5% of modern nuclear fuel has undergone fission. So, and that means that like 95% of the uranium in there is just regular uranium. There's a lot of caveats to that, but what you could do is you could recycle the fuel. If you could so the fuel, I'm oversimplifying a lot. The fuel can't maintain a chain reaction because that 5% depletes it a little bit, and because fission products from that tend to absorb neutrons, so they disrupt the chain reaction. You could theoretically chemically separate out that 5% and use that other 95% in specialized reactors, fast breeder reactors, fast burner reactors, which are slightly different than most of the reactors that we currently use, but not different enough to be prohibitive. But you could basically recycle this fuel and just dispose of this 5% that's disrupting the chain reaction. So that's exactly what reprocessing does. It chemically separates out different elements from the fuel so that you can recycle the fuel in different types of reactors, which is nice because this, if you recycle if you recycle 95% of our nuclear waste, then that reduces the volume of our waste by 95%. So this cube is all of a sudden 12 meters on each side. So that significantly reduces the volume of our waste, which may make it even easier to dispose of. What's more, there's a lot of value in that spent nuclear fuel. So there are, for example, those radioisotopes that make it radioactive have a lot of potentially useful purposes. So again, you can use fast reactors to recycle some of those isotopes, but things like technetium-99 are actually used for medical scans. Technetium-99 is interesting because it's our bodies have not evolved to use technetium for any biological process. Technetium isn't really present in nature in any significant quantity. So when our bodies encounter technetium, your body just slowly excretes it. That means that you can use technetium for things like heart scans, where you can inject someone with radioactive technetium, stand them in front of a radiation detector, and then you will be able to see where their blood flows and where it does not flow. So you can image blockages in the blood vessels, you can image heart valve functions. There's actually a huge technetium shortage, and there are some startup companies that are proposing to make technetium. So it's a very popular medical isotope. And it's highly useful, and because we just excrete it slowly over time, it doesn't cause any long-term dose. There are things like alpha emitters, which can be used to treat cancer. The very short explanation of that is that alpha particles tend to have, well, if you're trying to treat cancer, you want to kill the cancer cells but leave the healthy cells alive. Alpha particles from alpha radiation, which is what things like lutetium-177 emit, they travel about 6 cell widths in your body. So if you can get them to cancer cells, they're kind of like cancer-seeking missiles. So what you do is you attach things like lutetium to glucose. Cancer cells are very metabolically active. So the radioactive seeded glucose goes basically just to the cancer cells, and it just affects them and spares the other healthy cells. So if you take out all of the other useful isotopes from the fuel, technetium, the lutetium, all sorts of the other things, and use fast reactors to recycle it, then what's left? Well, then we only have about 3% of the original volume of our fuel left. And that 3% is mostly cesium and strontium-90, which actually have a 30-year half-life. So that means that we've reduced the inert point from over here to 2000 years to over here, which ends up being about 300 years. So the rule of thumb is that something is no longer radioactive, or something is considered stable after 10 half-lives. Because cesium and strontium have a 30-year half-life, that means that after 300 years, our reprocessed waste is now stable, is now safe. So then the question then becomes, instead of making a repository that holds the fuel for millions of years or thousands of years, can we build a structure to contain the waste for 300 years? I think the answer to that is yes, and history actually agrees with me. So can we safely store the waste for 300 years? Yes. Well, here are some structures or some things that are more than 300 years old. Buckingham Palace is 319 years old. This random house I found on Zillow in the UK was more than 500 years old, has an indoor sauna, which I think is really cool, but it's just some random house I found on Zillow. The president tree is 3,000 years old. I think it's the oldest tree in the States. I got that one off by an order of magnitude, but it's even older than 300 years. The oldest bridge in America is the Frankfurt Avenue Bridge just outside of Philadelphia, which is 327 years old. Lots of people drive over this bridge every day without even realizing how old it is. But my favorite example of all of these is the Lane House, which is the oldest building I forgot to look this up, either North or South Carolina. So the Lane House, uh, it's funny because the owners didn't know it was that old. They were actually using it as an Airbnb, or as a rental property, and they were remodeling it a little bit, and they removed some cheap plastic paneling at one point, and they found some wood underneath that looked really, really, really old. So they called someone, and then they got someone to date the wood, and they discovered that the house that they owned was actually more than 300 years old, and was the oldest home, the oldest structure in that state. So they were accidentally living in a structure that was more than 300 years old. So if you can accidentally have a structure that's more than 300 years old, I think it's very easy to build one and to engineer one to contain the waste for this long. So I think that reprocessing is a very ideal approach, because it recycles our fuel, it gets you a lot of valuable medical isotopes, it makes it easier to dispose of what's left. But the downside to reprocessing is the potential for nuclear proliferation, When you separate out isotopes, you can separate out plutonium from uranium, which could cause a potential weapons concern. I won't say too much more about that, but I will say that the general consensus in the nuclear engineering community is that reactor-produced plutonium is not that great for weapons. You either can't or make a weapon with it, or you can only make a small weapon with it because it's not produced under ideal conditions. You have to have very specialized reactors to make good plutonium for weapons, and common reactor plutonium is not that good. So I think that reprocessing is really a great approach. I'm not necessarily concerned about the possibility of nuclear proliferation that it brings, but that does scare some folks. Actually, some folks on the Blue Ribbon Commission were split about reprocessing, potentially because of that proliferation concern. So that is reprocessing. That is deep geological repositories. I think that we could end our presentation here, and those are perfectly acceptable approaches. But let's go a little bit farther and go into some of the more fun or less conventional approaches for disposing of nuclear waste, starting with ocean disposal. By ocean disposal, I mean subduction zone disposal. So there are subduction zones where one layer of the Earth's crust goes underneath another layer of the Earth's crust. So it's just it you basically plant the nuclear waste like seeds in the subduction zone, and it just gets sucked down, and it just completely goes underneath it. It's not coming up anymore. It just gets sucked down gradually and goes away, just like this very unfortunate scene in this movie. I apologize to folks in the audience who are traumatized by this scene, but it's basically just like that. It goes in the subduction zone and it's gone, goes into the Earth's mantle. So it is like planting radioactive seeds that just gradually get sucked into the Earth's core. And once the waste is there, it's gone. You don't need to worry about it being re-emitted or anything. The Earth's mantle is huge. It's not coming back. It's just completely gone. So subduction zone disposal is very effective, a bit expensive, but it's very effective. Folks are not proposing, when I say ocean disposal, I don't mean like throwing the waste in the ocean, like putting it in a blender, chopping it up and throwing it into the ocean. That's completely crazy. No nuclear engineer I know is proposing disposing of nuclear waste by just dumping it into the ocean without any controls. So how much radioactivity would it generate if we just dumped all of our nuclear waste into the ocean without any controls, right? We just didn't do subduction zone disposal. We just put the waste in a blender and dumped it in the ocean. So now you can vote on your machines on this one. And here's a hint. So the EPA's drinking water limit for tritium in drinking water is 20,000 picocuries per liter. So guess how many picocuries per liter we would get from dumping all of our waste in the ocean. And Uchenna, whenever you are ready to reveal the answer to this.
Okay, people are still submitting some answers, but I'll read out the percentages where they stand now. We have 50% for A, 28% for B, 18% for C, and 6% for D.
Cool. We have nuclear waste optimists because the most popular responses are A, and then the least popular response is D. So folks think it wouldn't generate that much radioactivity, which is correct. The correct answer is actually C. So the volume of the oceans is this large number, and we have that many picocuries in nuclear waste. So you divide those out and you get 708 picocuries per liter for our evil plan of dumping all of our nuclear waste in the ocean. Again, no one is considering this plan seriously, but it would actually work. It would actually be surprisingly effective. The oceans naturally contain 367 picocuries per liter of radioactivity, which means we would only triple the radioactivity of the oceans, which that's a very scary sentence. Saying we would triple the ocean radioactivity is sounds really bad, but I guarantee that a lot of people in the audience didn't realize that the oceans were naturally radioactive in the first place, and there's no controls over that. It doesn't cause anyone any harm. So if we triple a number that is close to zero, it's also a number that's close to zero. For what it's worth, the ocean water would still be drinkable according to the EPA radioactivity drinking limits. This limit's for tritium, so it's not completely apples to apples, but it's still, more than an order of magnitude below the limit. So this plan would be surprisingly effective. You could actually look at it. Doing this would barely change the amount of uranium in the ocean because the oceans are really, really, really big. So you wouldn't have any uranium's a heavy metal, and you wouldn't have any concerns about extra heavy metal in the ocean because uranium is already in the ocean in decent quantities. And actually, I calculated how much dose you would get from drinking 1 cup of our radioactive ocean water. It would be about 0.000016 millirems of dose, which which is approximately 1 second of your naturally occurring radiation dose. So I think, actually, no, I think 8 hours of 8 cups of water per day is like 1 second of your natural dose or something. So it's really nothing. It would not increase your radiation dose drinking all that radioactive water in any appreciable way. So this plan, as bad as it sounds, and the fact in this plan that no one is considering would actually work, which I thought was interesting. I thought was quite surprising. All right, second to last is space disposal. So what if we just want to eject the nuclear waste and launch it into space? So that brings us to question 6. What would be the total cost of space disposal of nuclear waste? So not to get ahead of myself, but the cost of space disposal has typically been prohibitive. So it's typically a very high cost, but how high? I want to see what you guys guess. So I'll move on. So I'll give you a couple minutes to vote on that so you can think about it, and I'll get the answers in a second. But I will say that there is a really interesting study on space nuclear waste disposal that NASA performed in 1978. You can Google it and get the report that NASA wrote. It's available for free. But they explored 5 different techniques for disposing of nuclear waste. So those techniques are putting the waste in orbit around the Earth at high Earth orbit, putting the waste in orbit around the moon, depositing the waste on the surface of the moon, so having like a lunar spent fuel repository, putting the waste in orbit around the sun at a radius of about 0.86 AU, or just launching the waste completely outside of the solar system entirely. So there are 5 different options. They all have their advantages and their disadvantages. In some of them, the waste is retrievable, which is nice. For example, if you don't reprocess it, but then decide that you want to reprocess it. Some of these methods rely on maintaining a stable orbit around the Earth, which orbits decay over time. So that could be a negative if you don't want to maintain that orbit. So some of these techniques rely on the waste vessel maintaining its integrity over time, which if you just launch it outside the solar system, you don't really care about. So there's pluses and minuses to each of these methods. And the cost of each method is based on the delta V. So the impulse, basically the amount of velocity you would need to get that rocket to put the waste into that specific location. More or less, all these methods have about the same delta V. Shooting the waste outside of the solar system would be the most expensive because you'd have the highest delta V that you need. But for the most part, they're pretty similar. I will note that the method that people think of when they hear of space disposal, which is shooting the waste into the sun, actually would be way more expensive than all of these methods. I think it was like 29,000 for the delta V. So it takes more energy to shoot the waste into the sun than to launch the waste entirely out of the solar system, which I thought was really interesting. And that's because the Earth gives us a lot of angular momentum. And to shoot something into the sun without it slingshotting, you have to remove a lot of that orbital momentum. So it takes a lot of energy to basically slow something down so that it can fall into the sun. But that's a summary of the NASA paper, which you can download and read more of. But how much would it cost? So Uchenna, now is a good time to reveal that answer.
All right. So for 1.6 billion, we had 4%. For 160 billion, we had 22%. For 1.6 trillion, we had 54%. And for 160 trillion, we had 20%.
All right, very cool. Yeah, it's cool to see that I was able to trip some people up here. It's usually not the biggest number on the answers, but yeah, this would actually cost $160 trillion to do. That's because our 88,000 metric tons of waste, right? It's we are limited in how much payload we can carry per launch, and we can only carry, I think it's like half of that payload from low Earth orbit to high Earth orbit. So there's not much waste we could get into high Earth orbit per launch. And this payload is actually reduced as well. It's reduced because you'd have to contain radiation shielding on the space shuttle to protect the astronauts from radiation from the waste. You'd also have to have thermal controls to keep the waste at a safe temperature, right? It's emitting energy because it's undergoing radioactive decay, so you have to control that energy release and not let it be too intense. And then also the other thing that limits that is the reentry protection. So this waste package, you can actually design nuclear waste packages so that they can re-enter the atmosphere safely. So you can basically turn this nuclear waste package into like the black box on an airplane. So you can actually make it with it involves like coating it with niobium metal and maybe some silicon carbide or something, but you can actually make it so that the waste is can can maintain integrity if the space shuttle were to blow up, for example. About 1 to 2% of space launches fail, which means that the spacecraft blows up usually. And you would have to engineer it so that the waste would be able to withstand the rocket blowing up without releasing radioisotopes. So, but you can, which surprised me, using that niobium structure, but that all that structure, all that stuff reduces the amount of waste you can carry per launch. So for the space shuttle, you'd need 100,000 launches, and at 1.5 billion per launch, that's $160 trillion to put our nuclear waste into space. However, there may be some ways around this. So if you reprocess the fuel, NASA estimated that you would reduce its volume by about a factor of 40. So then that reduces this number by a factor of 40 to only 4 trillion. And there's another approach, which is SpaceX. So the Falcon Heavy and the SpaceX Starship, other than being tongue twisters, can carry a lot more payload per dollar for the launch. So they're a lot more efficient at getting material into space. So I thought this was really interesting because if you use the hypothetical SpaceX Starship numbers, then for a cost of about $48 billion, you could potentially take all your nuclear waste into space. So that was really interesting. And it's weird that it's cool and interesting that this puts space disposal into the realm of being feasible with the amount of money in the nuclear waste fund, right? That 44 or so billion is all of a sudden kind of close to this number. So I thought it was interesting that space disposal of waste was more feasible than I thought it would be. So lastly, because I know we're getting close to the end, what's the last option for disposing of nuclear waste? And that is to do absolutely nothing. So nuclear waste, it's basically safe where it is right now. The waste is either in spent fuel pools, or as those fuel pools fill up, we move the waste to dry cask storage. So dry casks are these big, thick concrete casks which contain the nuclear waste. And after about, I believe, 4 years in these spent fuel storage pools, the waste has decayed enough so it's not producing that much heat, and it can actually be kept at a safe temperature outside, just cooled by the air around these casks without any active cooling mechanisms. These are big, thick concrete casks. The waste is just sitting there, not doing anything. Here's the waste from the main Yankee plant, where the plant generated basically all of Maine's electricity for 50 years. And it's a completely fine place to keep the waste for now. So I think that I would rather keep the waste here in these dry cask storage casks for now and then reprocess it later versus putting it into Yucca Mountain or putting it somewhere permanent where we just lose all that waste. We lose all the value, all the isotopes in that waste. So dry cask storage is also very feasible. So with that, I'm almost to the end of this presentation. So lastly, oh, this is the outline. Lastly, what do you think is the best option for nuclear waste disposal? Of the options we discussed today, I'm really curious to see what you all think is the best option. All right, there we go. So please submit your votes. And lastly, here's my name, my email address in case you have any questions or want to reach out to me about anything. And there's the name of my YouTube channel as well, Nuclear Engineering Lectures. Somehow that name was not taken, but I took it. And if you want to watch my videos on nuclear waste and get a more in-depth presentation than this one, there's the link. So with that, I appreciate you all paying attention, and I'm happy to answer any questions.
All right, thank you, Chris. First question, legacy nuclear waste could take the form of sludge, correct? And I think this person's maybe talking about Hanford tanks, Oak Ridge tanks, Idaho. What about that?
Yes. Yeah. So I know that reprocessing does create some radioactive sludges as well too. You get fission products and other things in those sludges. So that question is correct. I oversimplified for the presentation, but most of the waste, what people typically think of when they think of nuclear waste, is that spent fuel, that solid fuel.
All
So
right, in terms of repositories, what waste would be loaded first into a repository if it opened?
yeah, so I don't know the specific order in terms of the newest waste or the oldest waste. I would think that if we have a reprocessing plant, you'd want to prioritize reprocessing whatever has the most value or whatever gives you the most isotopes that you need right then and there. But typically, so Yucca Mountain, I will say the waste in Yucca Mountain would be the high level waste. So there's like low level waste in other forms, and that wouldn't be sent there. It'd be that post reactor fuel waste.
Okay. Can spent nuclear fuel be returned to an otherwise abandoned uranium mine, such as in Colorado, where I grew up?
Yeah, that's a really interesting question. That's a really interesting idea. So I would probably not, right? Because you have all that radioactivity in there, because you have all those fission products in there. If you were to reprocess it and separate the fission products and you had a bunch of leftover uranium, then I would see no problem with returning the uranium to that mine. However, I think that there's a lot of value in that uranium. You could use it as fuel in fast reactors, all the other actinides that are in there. So returning it to a mine is not really the best use of it, I would think.
Sure. Uchenna, do you want to tell us what the survey says from the last question?
Sure. So we have 23% for deep geological repositories, 57% for reprocessing or fast reactors, 1% for ocean disposal, 4% for space disposal, and 16% for do nothing for now.
Very cool.
All right, and the results show up there. All right,
Very
the storage rules you discussed, are they the same for both high level and low level waste, Chris?
No, I don't believe I don't know for certain since I haven't looked in detail into the regulations for low level waste. I think it's I would suspect it's probably different. I mean, low level waste is typically some items that are like contaminated or things that are activated to small amounts. And activated materials tend to have half-lives that are much shorter than spent nuclear fuel. For example, something that people actually don't realize is that a fusion power plant would actually produce more radioactivity than a fission power plant because you get neutrons from the fusion process, which would activate all the steel in that fusion reactor and make it radioactive. The difference there is that the half-life of that activated iron, the activated steel, is more like 12 years. So it's not millions of years or 30 years or 1,000 years. It's 12 years. So it'd be more radioactivity at first, but it would decay away more quickly. And that's the same thing with most types of low level waste. Typically decays away more quickly. You just have to keep it somewhere safe for the 10 half-lives.
All right, this is our last question because we got 2 more minutes, and we'll make it local since you're in New Mexico. The question is, can you talk about WIP, Waste Isolation Pilot Facility there in New Mexico, or the Waste Control Specialist in Andrews, Texas?
Yeah, so I actually have a bonus slide on WIP. I actually went inside of WIP. That's me right there
Okay.
after an ANS conference, and it's basically a salt mine, and you have these tunnels drilled into thick layers of salt. The idea being that, right, salt is really great at preventing water intrusion, and this is just a naturally enormous amount of salt deposits. So it's a great potential site for a nuclear waste repository. It contains the true waste, the transuranic DOE waste from the DOE programs. So kind of slightly different focus than Yucca Mountain waste, but it is a waste site similar in principle to Yucca Mountain. And yeah, I'm trying to be quick since I know that this is going to end soon, but it seems like a great place to put the waste. I believe there's an incident a couple years ago because they use kitty litter to absorb moisture in some of the packages there, and they used, I believe, organic kitty litter instead of inorganic kitty litter one time, which caused a reaction, produced some nitric acid and some gas that gas caused some overpressure and caused one of the little, it was actually just a 55-gallon drum of material. It caused it to just rupture to burp out some of that gas and release some radioactivity, which caused a lot of headaches and a lot of stuff to clean up. But I mean, I was down there shortly after that, and they had a little hall where we weren't allowed to go where that had happened, but we just went through the rest of WIP and looked at that. So,
All right, on that note, on cat litter, we'll leave the crowd. I appreciate y'all coming, and I thank Chris for all of his efforts. And we'll see you at the next ANS webinar. Thank you all.
thanks so much. Had fun.